in 1738, Euler presented to St. Petersburg Academy the proofs of some arithmetic theorems, where he gathered a family of quartic Diophantine equations whose impossibility can be established by infinite descent, often through clever use of Pythagorean triple parametrizations. Among them are a sum of difference of fourth powers equals a square, 2 times a sum of difference of fourth powers equals a square, a fourth power plus minus 4 times another fourth power equals a square, to which we may naturally add a fourth power plus minus 2 times another fourth power equals a square, and a fourth power plus minus 8 times another fourth power equals a square. In this video, we revisit these equations from a different angle. Instead of relying on Pythagorean parametrizations, we build descent arguments using only factorization, coprimality, modular constraints, and simple identities. The goal is to reveal how descent stops being linear and becomes cyclical. To end, we present a group of identities linking these quartic equations. We'll start with case 1, a sum of 2 fourth powers equals a square. Assume x, y, and z are coprime. Then x and y have opposite parity and z is odd. Otherwise, with x and y odd and z even, then a sum of 2 fourth powers is congruent to 2 modulo 4, which cannot be a square. So without loss of generality, let's assume x is odd and y even. Next, we factor x raised to the fourth. These two factors are coprime, since any common divisor divides the sum to z and difference to y squared. But since z and y squared are coprime and both factors are odd, then each factor is a fourth power. So write one factor as a raised to the fourth and the other factor as b raised to the fourth. Subtracting them gives a raised to the fourth minus b raised to the fourth equals twice y squared. Hence, a is bigger than b and both are odd. Since y is even, write y as 2 times y sub 1. Factoring gives that a divides the two factors on the right-hand side. Any common divisor divides the sum to a squared and difference to b squared. Given a and b's coprimality, inherited from the two factors analyzed in the previous paragraph, then these factors a squared minus b squared and a squared plus b squared have 2 as their greatest common divisor, since a and b are odd. But a squared plus b squared are congruent to 2 modulo 4. Hence, 4 divides a squared minus b squared, and 2 divides a squared plus b squared. Note, every factor is a square once we divide through by 2. So write a plus b as 2u squared, a minus b as 2v squared, and a squared plus b squared as twice w squared, with w odd. Substituting into the third equation and simplifying gives u raised to the fourth plus v raised to the fourth equals w squared. Therefore, we reach an equation of the same shape as the original and the same parity structure, but with smaller numbers, yielding a strict descent. Indeed, we note that w squared is smaller than y squared, which is smaller than y raised to the fourth, which is smaller than z squared. Note, the first inequality is strict since a is bigger than b, which is bigger than 0. They are both odd, hence a squared minus b squared is bigger or equal to 8. Conclusion. When we drop Pythagorean parametrizations, the descents stop being linear and become cyclical, moving through a closed loop linking equations of the form sum of 2 fourth powers equals a square, and the difference of 2 fourth powers equals twice a square. In the previous slide, we exhibit a cyclical descent linking equations of the form a sum of 2 fourth powers equals a square, and the difference of fourth powers equals twice a square. In this slide, we show how an equation of the form a sum of 2 fourth powers equals a square also fits in a different cyclical structure. While these transformations do not by themselves produce a descent, once a sum of 2 fourth powers equals a square is reached, the previous cyclical descent can be applied. We begin with an equation of the form a fourth power minus 4 times another fourth power equals a square. Now we construct the following identity. So if a fourth power minus 4 times another fourth power is indeed a square, then it produces an equation of this other form. A sum of 2/4 powers equals a square. But this is precisely the type of equation we have already shown to be impossible by descent in the previous slide. Therefore, the original equation cannot hold. We can instead apply the transformation to this new equation, constructing this other identity. If the sum of 2/4 powers were a square, this would produce a new equation of the same form as the original. Although this transformation does not yield smaller numbers, it preserves the same structural features, in particular parity, as the original equation. Note that a symmetric argument applies in the opposite sign case, linking equations of a form 4th power plus 4 times another 4th power equals a square, and a difference of 4th powers equals a square. Yet, we can produce a cyclical descent from the original equation without resorting to Pythagorean parametrization. We assume x, y, and z are coprime. Then x and z are odd. We factor x raised to the 4th minus z squared, giving this expression, and since both factors are even, each can be divided by 2. Any common divisor of these factors must divide their sum x squared and difference z squared. But since x squared and z are coprime, then the factors are coprime too, and each one is a 4th power. Therefore, we write x squared plus z equals 2 times a raised to the 4th, and x squared minus z equals 2 times b raised to the 4th, giving a raised to the 4th plus b raised to the 4th equals x squared, with a, b, and x coprime, and a and b of opposite parity. Also, z equals a raised to the 4th minus b raised to the 4th, which will be useful when finally applying the descent. Assume b even, hence a odd, and write b as 2 times b sub 1. Then b raised to the 4th equals 16 times b sub 1 raised to the 4th, which factors as x minus a squared times x plus a squared. Any common divisor of these two factors must divide the sum 2x and difference 2a squared. Since x and a are coprime and both factors are even, it follows that the greatest common divisor of the factors is 2. Moreover, x plus a squared is congruent to 2 modulo 4. Hence, 8 divides x minus a squared and 2 divides x plus a squared. The factors are coprime, so each is a 4th power. We write x plus a squared as 2 times u raised to the 4th and x minus a squared as 8 times v raised to the 4th. Subtracting yields a squared equals u raised to the 4th minus 4 times v raised to the 4th, with the same shape and parity structure as the original. Moreover, this new equation is smaller than the original one, since a squared is smaller than z squared, thus giving a descent. Recall that z equals a raised to the 4th minus b raised to the 4th, and since a is bigger than b, which is bigger than 0, we have that a squared is smaller than a squared plus b squared, which is smaller than z. A similar cyclical structure links equations of a form a 4th power plus minus 8 times another 4th power equals a square, and a 4th power minus plus 2 times another 4th power equals a square, using a pair of identities designed to connect the two forms. Again, these transformations do not by themselves produce a descent, but a descent for the first equation can be carried out without using Pythagorean parametrization. Case x raised to the 4th plus 8 times y raised to the 4th equals z squared. Assume x, y, and z are coprime. Factoring y raised to the 4th gives z minus x squared over 4 times z plus x squared over 2. Since x and z are odd and z plus x squared is congruent to 2 modulo 4. Analyzing the sum and difference of the factors, we deduce that z minus x squared over 2 and z plus x squared over 2 are coprime. Hence, each of the factors of y raised to the 4th are a 4th power. Writing z plus x squared equals 2 times a raised to the 4th and z minus x squared equals 4 times b raised to the 4th gives a raised to the fourth minus 2 times b raised to the fourth equals x squared, with a, b, and x co-prime, and a odd, and b of either parity. Also, we deduce that z is equals to a raised to the fourth plus 2 times b raised to the fourth. The equation a raised to the fourth minus 2 times b raised to the fourth equals x squared has a, b, and x co-prime. Factoring gives b raised to the fourth equals a squared minus x times a squared plus x over 2, since a and x are odd and a squared plus x is congruent to 2 modulo 4. Again, analyzing sum of the difference of the factors, we deduce that they are co-prime. Hence, each one is a fourth power. So we can write a squared plus x equals 2 times u raised to the fourth, and a squared minus x equals v raised to the fourth, with u odd. Adding up gives 2 times a squared equals 2 times u raised to the fourth plus v raised to the fourth. Hence, v is even, so we write v as 2 times v sub 1. Simplifying yields that a squared equals u raised to the fourth plus a times v sub 1 raised to the fourth. An equation of the same shape and parity structure as the original, and a strict descent, since u raised to the fourth plus a times v sub 1 raised to the fourth equals a squared, which is smaller than a raised to the fourth plus 2 times b raised to the fourth, which equals z, which is smaller than c squared, which is x raised to the fourth minus 8 times y raised to the fourth. Last, a cyclical structure links equations of the forms a difference of fourth powers equals a square, a sum of fourth powers equals twice a square, and a fourth power plus 4 times another fourth power equals a square. As in previous cases, we produce a descent without using Pythagorean parametrization. We start with x raised to the fourth minus y raised to the fourth equals a square, with x, y, and z co-prime, then z must be odd, and x and y of opposite parity. Factoring z squared gives these three factors where all are odd. Then x squared minus y squared and x squared plus y squared are co-prime, since any common divisor divides the sum to x squared and difference to y squared. Similarly, x minus y and x plus y are co-prime. Hence, each factor is a square. We write x plus y as a squared, x minus y as b squared, and x squared plus y squared equals c squared. Thus, 2x equals a squared plus b squared, and 2y equals a squared minus b squared. Hence, when substituting in the third equation, gives a raised to the fourth plus b raised to the fourth equals twice c squared, with a, b, and c odd. So we have this equation, a raised to the fourth plus b raised to the fourth equals twice c squared. Squaring gives 4 times c raised to the fourth equals the square of a raised to the fourth minus b squared plus 4 times the square of ab. Since a and b are odd, we can divide through by 4, yielding c raised to the fourth equals the square of a raised to the fourth minus b raised to the fourth over 2 plus the square of ab. We write d as a raised to the fourth minus b raised to the fourth over 2. So now we are back to a difference of fourth powers equals a square, but this time the fourth powers have equal parity and the square is even. So we need to go through the cyclical descent one more time. Recall that a, b, and c are co-prime, with c and a times b odd. Then d is even. Factoring d squared yields these three factors, which are all even. Then c squared minus the square of a times b and c squared plus the square of a times b have 2 as the greatest common divisor, since any common divisor divides the sum to c squared and difference 2 times the square of a times b. Similarly, 2 is the greatest common divisor of c minus a times b and c plus a times b. But c squared and the square of a times b is congruent to 2 modulo 4, c squared minus the square of a times b is divisible by 8, and c plus a times b is congruent to 2 modulo 4. Hence, 4 divides d, so we write d as 4 times d sub 1. Then, d sub 1 squared can be written as this, c minus a times b over 4 times c plus a times b over 2, times c squared plus the square of a times b over 2. Well, these factors are pairwise coprime, hence each is a square. We write c times a plus b as 2 times u squared, c minus a times b as 4 times v squared, and c squared plus the square of a times b as 2 times w squared. Thus, c equals u squared plus 2 times v squared, a times v equals u squared minus 2 times v squared. Hence, we substitute in the third equation, giving u raised to the fourth plus 4 times v raised to the fourth equals w squared, with u, v, and w odd and coprime. In this next step, we square the equation, giving w raised to the fourth equals the square of u raised to the fourth minus 4 times v raised to the fourth plus the fourth power of 2 times u times v. Hence, in this last equation, we have a difference of fourth powers equals a square. This time, the square is odd, and the fourth powers have opposite parity, just like the initial equation. We arrive at an equation of the same shape and parity structure as the original and a strict descent, since u raised to the fourth minus 4 times v raised to the fourth is smaller than w squared, which is smaller than 2 times c squared, which is smaller than z squared, since c squared is equal to x squared plus y squared, and x squared minus y squared is bigger or equal to 3. In this final slide, we present the identities used in the preceding cyclical descent arguments, along with a few additional ones. Together, they form a family of identities linking Euler's quartic equations. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.